Hello everyone and welcome to this quick video on the fabrication workflow for 3D printers. The first thing you need to understand is that our fabrication workflow is broken up into two parts. The first part, which you already know, is CAD, which is computer aided design. Softwares like AutoCAD, Rhino, Vectorworks, 3ds Max, Revit, whatever you're using, this is your CAD software. The next part and the crucial part for fabrication is what's called CAM, and that's computer aided manufacturing. CAM is the software that speaks the language of your fabrication tool. So for example, when we're talking to a 3D printer, the 3D printer doesn't understand your Rhino model. What it understands is how far to move in the X, Y, and Z direction, how much material to lay down in terms of its thickness, and how fast to do so. And so what we need to do is convert our drawing or model into that language that our machine will understand. Now every 3D printer is different and every fabricator will have a different way they like to work in terms of their workflow, so you need to send them an email and ask what specific file type they prefer. If you are the fabricator and you're working directly with the 3D printing machine yourself, there will be a specific software that you need to use. Generally speaking though, 3D printers tend to understand one of a few file types, including the STL, stereolithography, the OBJ, the object, and even sometimes a DXF. In our previous video on the digital fabrication tool types, we talked about the idea of scaffolding and whether or not we would have a solid model or whether or not it's full of scaffolding on the inside, making it relatively hollow and using up less material. Another thing we need to consider is the resolution of our print. And you might be thinking, well, of course I want it to be perfectly smooth and not show up any edges whatsoever. Why not? Well, really it's dependent on the time and the cost you are willing to part on this 3D print. For example, the same object printed at 300 microns might take an hour to print, but it's super lumpy and bumpy. The same object at 25 microns, much thinner, might give you a smooth and seamless look, but it could take 12 hours to print. And of course, we're paying by the minute here, so we really need to keep that in mind. It's important to find the right balance between what is the ultimate resolution you can achieve and what can you afford in terms of time and financial outlay. Now, because we're dealing with additive construction instead of subtractive construction, like we talked about in the last video, there's another thing we need to consider with our 3D printed models, and that is support. The typical FDM printer that we'll be using for a lot of our modeling purposes is going to be extruding out PLA filament vertically downwards. And so that means if we get to any point in our model where there is no model beneath where we're extruding out, we're effectively extruding filament out into air. And so you can guess what's going to happen next: lots of noodles. So the reason this is important to understand now is because when we get into the next phase of actually putting our Rhino model into the software that the 3D printer uses, that software is going to add supports wherever it is needed. Now, typically the supports are easy to cut away with a scalpel or with a set of pliers after the model is finished, and so that's fine. But other times we have a model with lots of intricate detail and we have some overhangs where we don't really want to have that scaffolding or that support system in there. It's hard to get to, it's going to look messy, and it's going to leave something in our design that isn't actually there and shouldn't be in our prototype. Now, there's no real workaround for this because the 3D printer must have its supports in order to be able to function properly without failure. So you need to decide, is it really important for me to have this overhang here? If so, am I going to be able to cut away these support systems? If not, do I really need to have these overhangs? Is there another way I can design this so I get the same aesthetic look without having to deal with these structures later? One change you might consider would be the angle of your overhang. If you have a steeper angle or a more vertical angle, then it's more likely to support itself from below. Or another option you might consider would be to actually make the overhang solid underneath. So instead of having a cavity below, all of the structure and support system below the overhang is now made solid, and so we don't have to see the support system anymore. Alright, so those are the three main things I want you to consider while we're developing our model. Is it going to be solid or hollow? What's my resolution? And do I have any overhangs? If so, can I get around them, or am I happy to have some supports? Once we've got that sorted, we need to convert our Rhino model into an OBJ, an STL, and a DXF. Let's have a look at how to do that now. Okay, so we're in Rhino now, and there's a few things that we need to check over before we are ready for 3D printing. The number one thing for 3D printing, very much the same as CNCing, is ensuring that we are dealing with a pure solid. So of course, if we click on our geometry, we can see one closed surface added to selection. And if we go over to our details tab, we should see it is a valid surface and a closed surface, and that's going to tell us that it is a solid. This is critical for 3D printers as they don't understand ultra thin surfaces that we get from Rhino. They only understand the solids, so they need to see one geometry closed over the top of itself, just like we have this one here. If you are unsure of whether your geometry is closed or it's not saying it's completely closed, what you can do is select your geometry, head up to Analyze, Edge Tools, and Show Edges. And just like we talked about in a previous video, any edge that is naked, i.e. not completely closing against another edge, will show up pink here, provided that you've got that. And you can even zoom to the naked edges as well, and that will take you to all of the unjoined edges in your geometry. And then what you'd need to do from there is do either a merge or a blend or a loft to make sure you're closing up all of your gaps. Then join everything together and make sure it is a solid. So that's the first and most basic geometry for taking to 3D printing. We've got something and it's solid and ready to go. Let's have a look at this one here. So we've got the same thing, but now we've added some balls inside of our bag here as well. So what we would need to do is ensure that we are dealing with one geometry still. So even though these are all solids, which is great for our 3D printer, what the 3D printer will do is it will separate each one of these spheres out. It will 3D print them all individually and away from your bag, which is not what you want to do. You want them all to be inside there. So what we need to do to make sure we're ready to go is select everything and then go over to our Boolean Union. Click on that, make sure everything is solid, and then we should be able to click on this and not be able to select any of the individual spheres, which we can see now. And we can go over to details, and we've got a closed valid poly surface. So we know now that this is going to be treated as one solid by the 3D printer. Alright, now let's go over to a more complex geometry. So we can see we have an arrayed surface here, which is made up of a bunch of these smaller little surfaces, and together they're going to make a complex geometry which is quite tactile and haptic, something really interesting. First problem we noticed before going to our 3D printer is that these are made of individual open surfaces, so the 3D printer is not going to be able to read any of this. Remember, in Rhino these are infinitely thin, so they don't even have a geometry to them while they're still surfaces. So I would be making these into surfaces straight away. Got a couple of options here. I can offset my surface, flip it downwards so that it's going to offset inside itself, and I would do this by about 1 millimeter. And enter, and then we have a solid. So we can see, we go over to our details tab, we've got a closed solid poly surface. Great. So that would be one option, and then I just redo that array again based on this one geometry. But I can foresee another problem. So we know that our 3D printer is going to be printing from the bottom upwards. If we were dealing with an SLA printer where we're printing from the top downwards, we might not have a problem because we're going from this bit all the way down the slopes until we get to the bottom. Typically we're going to be dealing with an FDM printer using PLA, which is extruding vertically upwards. Now obviously you need to ask your fabricator what they're doing, but if you are using FDM with PLA, this sort of geometry is going to become a problem. It will start off fine down here and be able to go all the way around. It's pretty flat around there, but you'll see as we get to these points here, we do have no material touching the ground. So if this is our flat plane down here, we're going to end up with the 3D printer trying to print geometry on top of air. So that is going to cause an issue for us. So we need to get rid of these horizontal overhangs and make sure we've got more vertical areas. Vertical areas mean the material underneath itself is going to support the next layer of material. So we can see this will go up fine. This is pretty steep in terms of the angle here, and that should be okay. It's these horizontal areas that come away from the ground plane that are going to cause us some mischief. So we've got a couple of options. Let's undo that offset. I'm going to bring my shell out here. And then what I'm going to do is, instead of creating an offset, I'm actually just going to copy one vertically down. So I hit vertical, type in 1 mil again, and there we have it. We've got a copy on the inside here. I'm just going to pull this one out by 20 mil so we can see what's going on. Now we know that our trouble area is going to be this horizontality here. So what we're going to try and do is fix that. Got a bit of horizontality on the back here as well. So what we can do is we can turn our control points on, and I'm going to bring these points down a bit. And then the next thing I'm going to do is actually bring these points inwards a bit inside there as well. So I'm still going to have that cavity inside, but I'm just trying to create more verticality and less horizontality inside this thing. So we can see, compared to the original slope, we've got a lot steeper inside there now, and we don't have that big horizontal overhang at the back. That's now been turned into that sweep inside there. Okay, so that's that. Next thing we can do is actually just create an additional geometry to remove some of this horizontal surface that we have inside here. So what I'm going to do is I'm going to take a slab at 1 millimeter, and that's going to be our offset height between these two anyway. So that's going to mean that it's taking out all of this slack that would be inside there and now covering it up with a base. So we end up with the only horizontal portions that we have to be worried about now are the ones inside this cavity in there. If you're still worried, what you can do is just continue to massage that until you get to a point where you're happy that we don't have much horizontality at all. You can even rebuild your surface if you wanted to have a bit more control over what's going on and play with some of the specific points inside there. And we remember from previous exercises, the more points we had to control, the more we can play around with some of these geometries as well. But really you would massage that down until you're happy. Now, if you were the one doing the 3D printing yourself, what I would recommend you do is actually create a few different iterations to test this. You can do one that is very similar to the original object, see how much that it fails by, and then that will give you an understanding of how much editing you need to do. And then I would do a super strict one, like this one here, or maybe even stricter, and then some iterations in between that, so we can see, okay, well, it didn't actually need to be this strict. We could use the second or third degree in between those two, and that was able to still get us the result we want, whereas we didn't have to worry about failure on the inside there. So 3D printing is very much about trial and error and testing until you know that you have the right settings. Okay, so I'm happy with this one. Now what I'm going to do is loft these front curves. There we are. Then we need to do some more loft, so I'm just going to move our slab downwards out of the way for now. Loft. Alright, now that we have all of our lofts complete, we can go ahead and grab just our finished surfaces, type in join to join them all together. That should now be a closed poly surface. Let's bring our slab back up to where it's supposed to be, and then we can do a Boolean union to join them all together, and we now have one object here that is ready to go. And so we can see we've kept our original outside geometry. We've made our geometry a little bit easier to 3D print, less likely to fail. And also, if we do have to add any structural strength inside there with any supports, it's going to be much easier to get them out of this shallower hole that we have here than it would have been inside this big deep cavity out the back of there as well. So we would then move this back into position and then follow our array tool again. Delete all of these first, of course, and then follow with an array. Okay, let's have a look at one more now. This time we're going to look at a bit more of an assembly typology. So once again, I'll move my camera so we can see what we're doing into here. Okay, so we've got a biomimicry typology here, looking at some interesting geometry over the top of a hex tile, which has got some grooves and nice interesting filleting going on as well. Now, when we have a geometry like this, which is made up of multiple parts, it's not as conducive to 3D printing as something like this, where we can turn all of our geometries into one geometry by just booleaning them all together. These geometries don't actually touch each other. They have a gap between each one, and so it's going to make it really difficult. Of course, we can boolean this down to its base, and then we can 3D print the whole thing like this. However, the gap between here and here is monstrous. We're going to end up with so much scaffolding and support system underneath here that it's just not going to be worth our time. We're going to spend so much of it just trying to clean it all up and make it look the way we want it to. And really, with that much scaffolding in there, it's going to look really different to this beautiful smooth product that we have here. So what we want to do if we have a geometry like this, which is made up of multiple parts, is think of it like we do on the laser cutter video as an assembly method. So rather than constructing it out of one solid part, what we would do is break this down into its core units, into units that can be easily 3D printed, and then put them back together once they've all been complete. So first thing I would do is actually just make this base ready to have this geometry inserted into it later. So what I'm going to do is make a copy of my tulips that I have on top of here, just move them out of the way for now. Then I'm going to do a Boolean difference command so that I can subtract these out of my base that I have here. Okay, so first thing we go is to Boolean difference. What are we going to subtract from? That's our base. What are we going to subtract with? That's our tulips. We press enter. And there we have it. We zoom in and we can see we now have these beautiful little slots inside our base here where we're going to be able to put our tulips back into. Now that I have removed the tulips, something else occurs to me. Now, while I could 3D print this, there are better tools to come up with this geometry, namely a CNC. We've got a lot of smooth curves here. It's kind of a repeated form around each axis. We can see that a CNC would be able to produce this probably easier than a 3D printer in a much shorter amount of time with a higher quality finish. So what we would do in that case is actually split this into a hybrid technology or hybrid fabrication technique. We would have this part taken to the fabricator, presumably the same fabricator, and said, well, can you please make this on the CNC? And please understand that these circles here, these holes that we have inside this base, need to have a similar tolerance to what is going on at the bottom of our tulips here. We want these tulips to slot nicely into this base with some rigidity, and they'll be able to do that for you. So we've got that separate base now ready to go with its holes already taken out. Next thing we would want to do is think about how this is going to be made, these tulips. Now, what we can do is get it made just like this, but we're going to end up with the same problem where we have a whole bunch of vertical struts. We could turn it over by 180 degrees and have it made this way, but we'll still end up with a lot of struts inside there that we're going to need to clean out, and it's going to get pretty hard to do once we get into this tight geometry we have up the top there. So what I would actually recommend with an assembly unit like this is actually just get each part 3D printed individually, just like we have here. So we would flatten this out, lay it on the bed, and you would tell the fabricator that the most important surface for you is the tip of the tulip. So please align all of my supports and my structure along this bend here. And they might say to you, well, this is too small here. It's going to be quite fragile, might snap if we put our structures there. In which case you would say, okay, no problem. Lie that down flat and then just try and arrange my tulip so it doesn't have too much structure on the front. And then I'd be able to sand down this big side here without having to worry about anything on that edge there. We would then do that 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Once we have each of those, we can then just slot that right into our CNC base. So the only thing we really need to check then is to make sure, just like with our other 3D components, is that each element is solid and ready to go. So yes, closed surface, yes, valid closed solid. So this one is perfect and ready to go for the CNC. Then if we're going to use this method where they're all laid down, we can delete that because we'll just end up telling the fabricator that we want 9 of these in our PDF sheet. And so all we need to do is check details again, and once again close solid poly surface. So that is fine and ready to go. Alright, so the next thing we need to do is actually export it out into the file types that we need for 3D printing and CNCing. Fortunately, they are most of the time the same file type. We use a STL, a DXF, and an OBJ file. So let's do each one of those now. What we would do is we would select everything that we want to be exported, go up to export selected, we would do it as a DXF, and then you've got a couple of options here. Typically default is fine, but it's always good to ask your fabricator as well. Sometimes they might prefer everything to be converted to cam metric or polylines, whatever they might need. So you do that as your DXF. Next one you go up to is your STL, which is your stereolithography. Again, this is dependent on what they would like in terms of their output, so you can ask them as well. And then finally we have our OBJ file, which is this one inside here, and then formatting once again you can ask, but usually the defaults are fine for that point there. And the next thing we want to do is make some screenshots ready to take into Illustrator so we can put together an instructions sheet for our fabricator. So we go up into View, Display Options, and remember we went through this in our previous video, so I'm just going to do it quickly again now. And then we have our white background, so we can go ahead to View, Capture, to File, and we go ahead with uncheck that, so we're on a white background. 1080 is fine. Okay, so I'm in Illustrator now, and I've brought in all of my imagery from Rhino, sized it all up, and put together an instruction sheet. Now, because I am working with two different types of fabrication, a hybrid type, I've already spoken with my fabricator. I've already asked them whether they have both of the tooling types for CNC and 3D printing. They've said yes, and so now I've put together an instruction sheet based on that. So I've said I need one of these bases to be CNC milled. It's going to be made out of solid pine as the material, and I'd like them to use a finishing bit after cutting it down so that they can smooth down the surface and make it look much nicer, much less rough. Next thing we have is our 9 tulips. These are to be 3D printed. The material is black PLA, and the resolution I want this printed at is 100 microns. Next thing we have is some instructions about the tolerances. So here we've noted that these holes, which are inside our base, are 5 millimeters in diameter. They are 15 millimeters deep, and they need to fit the tulip ends to a tight tolerance. They need to be tight, but still be able to be removed by hand. So that gives them an understanding of what we're trying to do, what we're trying to achieve there. We've also got some dimensions of the tulips as well. And then we've asked if they can place the supports of the tulip on the head, on the underside here, which would be a much easier place to sand and much less delicate than the actual frond of the tulip as well. Then we have 2 assembled views so that the fabricator knows what we're trying to achieve from all of these parts. Once they're assembled, this is what they're going to look like, and that gives them a better idea of what it is that they're making in terms of its 3-dimensional geometry. So we've got a top view here, and this also gives them some dimensions. They're going to receive your files at 1:1 scale anyway, but I like to put in some dimensions just to make sure that what they've received matches what the output is going to be. Sometimes something can happen with the files, and so they can double check the scales and make sure that they are correct before going to print. We've got a side view as well, and together this gives us an understanding of what it is that we're doing. Finally, I've got my name and number here on the sheet, so if while they're fabricating they come across any problems or have any questions for seeking clarity, they can give me a call while they're doing that. Once all of that's done, we would save this as a PDF and then submit that with our other 4 files. So we have the DXF, the STL, the OBJ, and the PDF instruction file together. That should be everything that your 3D printer or fabricator needs to produce your prototype. Alright, so there's one more step we need to deal with now. Once we get our parts back from the fabricator, our 3D prints need a little bit of extra attention than we would have to do with our laser and our CNC. With the laser, we'll just have to wipe down our edges and then glue everything together. The CNC, we might have to do some sanding, but with the 3D printer, it's a little bit more involved. The first step is that we'll need to clip away all of the support structures. Then you might need to fillet off some of the sharp edges using a scalpel, and remember to be very careful in doing this. Then we need to deal with the resolution and find a way to smooth out all of those grooves we had from our low resolution part. We've got a couple of options for smoothing out the grooves. A lot of people online will use acetone, but I want to make particularly clear that this is a last resort and I don't really recommend it. It can actually melt your parts as well as being very, very toxic. I like to recommend some good old-fashioned filing to take down some of those sharp edges, especially if you can get your hands on some of these little files. Even a nail file will get most of that off for you. On larger areas, you can use some wet to dry sandpaper as well, and that'll come up pretty smooth. But sometimes we're dealing with areas that are a little bit too hard to get to with either the file or the sandpaper. Fantastic way I've found online to get around this is to use a mixture of spray paint and polyurethane. What you want to do is spray a thicker than usual coat of any color you want over the top of your model with spray paint, then quickly add a top layer of the polyurethane as a coat. Allow it to dry for 20 minutes to an hour and then repeat this process 5 more times until you've got a thick coat, making everything nice and smooth with much less visible grooves. Okay, so that's all for our video on 3D printing fabrication workflow. Remember to pay special attention to the resolution of your model that you desire, the angles of overhangs that you have inside your model, where the structure is going to go, and how to optimize your part for the best possible outcome when it comes back from the fabricator. As always, if you have any questions, please feel free to ask myself or any of your tutors, all of whom have plenty of experience with 3D digital fabrication. Another wealth of information is, of course, your chosen fabricator. They will know their machines and their software much better than we do, so if you are having any issues, please feel free to reach out. Let them know what you're doing, what you're trying to achieve, and what you might be struggling with, and I'm certain they will be able to help you get there. That's all for now, everyone. Happy prototyping.